We're taking a look at indefinite integrals and net change, and this is the first part, and we'll just look at the indefinite integrals. Here is your schedule, almost done. We're looking at definite and indefinite integrals. Just a recap of the fundamental theorem of calculus. Part 1 says that if f is continuous on the closed interval, then the definite integral from a to x, which is somewhere between a and b, is an antiderivative of f. Part 2 says if f is continuous on that closed interval ab, then the definite interval of f of x can be found by evaluating capital F of b minus capital F of a, where capital F is an antiderivative of small f. So that is, remember, the antiderivative of functions such that the derivative, capital F prime, is equal to small f of x. So the indefinite integral is called indefinite because we're not specifying an interval on which we want to find an area under a curve or total change under a curve. If we have boundaries, an interval that we're defining, then we call this a definite integral, and it yields a number, a specific number, which represents the net area under the curve or a total change in some quantity that you're graphing. If we do not have boundaries, then we're not defining a specific interval on this curve. And so, of course, we can't find a specific area because we don't know which part of the curve we're interested in. So this is called an indefinite integral. And what results from that is a function or a family of functions. And then a little bit more notation, when we have a definite integral, we can also write it like this, that it is the indefinite integral evaluated between b and a. It's just a little bit of notation. Here is a table of indefinite integrals, and note that this is really a table of antiderivatives, and you know some of these things already. For example, here is the reverse power rule. So you might have to keep coming back to this to refresh your memory about how to think in reverse, going from integrals and antiderivatives to derivatives. So let's do some examples. These are the examples we're gonna do, and you could pause here and try to do them all and then come back, or you can go through them one by one. So here is the first one, and again, if you haven't given it a shot already, do so before you take a look at the answer, which is coming up right now. We're going to take the indefinite integral, and for this particular one, remember, we're finding antiderivatives, so for this we're going to use the reverse power rule, and I've written it out the long way around. We're going to simplify, and then simplify even farther. And don't forget to add your arbitrary constant, because remember, this is an indefinite integral, so we're looking for the most general antiderivative. Let's go on to a second example. Again, pause if you haven't tried it. Here is the answer. So the first thing we want to do is like a little pre-processing. We want to remove this from the radical notation and make that a rational exponent, and then apply the power rule, the reverse power rule, and then simplify. And again, don't forget the arbitrary constant. All right, here's another one. And I've already put the answer up. So hopefully you will get the same answer as this. Again, this one is just an application of the reverse power rule and simplifying. All right, this one we're going to have to do a little work to start with to get it in a form where we can find the antiderivative. There are no quotient rules or product rules for finding an antiderivative. So right now it's in a form that we cannot work with. So looking at the answer, the first step I'm going to do is I'm going to take that denominator, x, and that is really, I'm going to move that up to the numerator as an x to the minus 1. Then I'm going to distribute that x to the minus 1, so I'm multiplying that by each one of my terms. And we'll simplify that a little bit more. And now I'm ready to find the antiderivative. Now on that first term, x to the minus 1, remember that is an exception. You cannot apply the reverse power rule to that. The antiderivative of x to the minus 1 is the natural log of x. And then the other two, you can apply the reverse power rule and simplify to get the final answer. Okay, another example, and again, we have to look at this in a slightly different way. You see that term 1 over x squared plus 1. Now that is not in a form we can work with, and even if you transform that to the quantity x squared plus 1 to the minus 1, you still can't work with that to find an antiderivative. So here's where I suggest you go back and you look at that table of antiderivatives to see if that appears, and indeed it does appear. In fact, 1 over x squared plus 1 is the antiderivative of, the arctangent is the antiderivative of 1 over x squared plus 1. So the rest, you apply the reverse power rule, and you've got your answer. And final example, we're going to do a little work to start with, not much. We're going to distribute that secant t to get secant squared t plus secant of t tan t. Go look at the table of antiderivatives, and you'll find that tangent of t has the derivative of secant squared. So your antiderivative of secant squared is tan t. And the secant t, tan t, the antiderivative is secant of t plus your arbitrary constant.